హలో సార్ ప్రభాకర్ గారు. ఓకే.
Gangadhar sir.
Yes, sir.
Sir,
Yes,
yes.
sir.
I think we can start, sir. Already we are waiting from past.
Okay, sir. Sure.
Let us start, sir.
Okay, sir. So it's already late, so we are going to start the today's class. So in the
Yes, sir.
last class, okay. Thank you, sir. Good evening, everyone. Thank you for joining the today's session of computational fluid dynamics, the basics. In the last class, I just give you a brief overview what we studied in the last class. This is we just understood what is the importance of computational fluid dynamics, that is also called as CFD in the last class, and what are the key governing equations, and we did not derive anything or we did not see, and what is the importance of this computational analysis. Everything we discussed and different types of flow field I just stated, but we can see all these kind of flow fields in detail later on, and different governing equations and partial differential equations, everything that a brief overview uh, I had given in the last class. So in this class, we are going to see uh, the vector calculus. This is our today's topic. So let's start. What is this vector calculus? So in the vector itself is basically stating it as a three-dimensional space. It can be a Cartesian, it can be a spherical, or it can be a cylindrical coordinates. Suppose if I have a Cartesian coordinates, this is my x coordinate, this is my y coordinate, this is my z coordinate. And if I want to indicate a position vector in the space, suppose I want to state a particle is here in the x, y, z dimensions. Okay, I will just draw a line directing from the origin. This is my origin and this is my point P in the space. And I will indicate this is a vector, OP vector. OP vector as x I cap. That means you need to travel x distance of this much length from here to here, and you have to travel y distance of y j cap from this point to this point, and z j cap. It is in the plane perpendicular to sometime. Sometime. It is on the plane perpendicular to the our paper. So we need to move in the z direction also, x I cap plus y j cap plus z k cap. So this is the OP vector. In this OP vector, we are able to see that what are the details of this position at some distance from the origin using this vector notation, that is x I cap. I cap means the unit vector in the x direction, while j cap is the unit vector in the y direction, and k cap is the unit vector in the z direction. This is how you already know these basics from your mathematics or your physics, how to define a position vector. And if it is a velocity vector say v bar, you will designate it as u I cap plus v j cap plus w k cap. What are these u, v, w? Suppose if a particle is moving in a three-dimensional flow field, then you just try to analyze its velocity vectors or velocity parameters in x, y, z directions, and if you are able to measure the velocity parameters in x direction, y direction, and z direction, those corresponding values are itself as u, v, w we are measuring. So this is very important vector form that we see in the complete fluid mechanics course or in the complete CFD course. Everywhere we play mostly with vectors, tensors. So it is very important to understand why the velocity vector is written in this format and how it is vector rotation is useful for our further analysis in the CFD course. So whatever the velocity values, suppose a complete magnitude is like this. Suppose it's moving at 10 meters per second, but at the same time, you have x direction is this way, y direction is this way, and z direction is this way. You can see the projections of this. It is moving both in three-dimensional like this with the 10 meters per second. So some component in the x direction, some component in the y direction, and some component in the z direction. If you resolve all these directions of this actual velocity vector, you will get the u, v, and w components. But how to resolve? What are the operations that we use? Everything will be included in this vector calculus. So I will just give you the brief interview or brief overview of this vector calculus. Let's say if you have a vector u, v, w, one can write in this matrix format as v equals to u, v, and w. Because I have a u vector, v vector, and w vector. So I'm indicating it as v is equals to u, v, and w. Okay. And then vector operations can be involved as a matrix operation. Those details we can see it later. But vectors can be transformed to the matrix for our easy manipulations in handling the data in our computational fluid dynamics. This symbol represents the modulus of your velocity vector. How do you define the modulus of velocity vector? It is the magnitude of the vector irrespective of its direction. That if you are representing a vector like this, v bar equals to u I cap, v j cap, and w k cap, you are representing its both magnitude and direction. But if you are representing like this, you are only representing its value, that is u square plus v square plus w square. Here, you are converting that vector into the only we are just identifying the vector's magnitude. What is the value or what is the intensity of that velocity without bothering about its direction, whether it is going in x direction or y direction or z direction. We are not bothering. We are just finding its absolute value. Okay. So vector properties are like this. I will just give you one more brief introduction of this vector property. Suppose you have a v1 vector plus v2 vector. If you are adding this, where v1 can be written as u1 I cap plus v1 j cap plus w1 k cap. If you are going to add these two, u2 I cap plus v2 j cap plus w2 k cap. It is just one-to-one addition. That is u1 plus u2 I cap plus v1 plus v2 j cap plus w1 plus w2 k cap. This is what your vector addition. It is valid for velocity. Any vector, it is valid. So these are your common properties of a vector that you had already seen in your basics of mathematics, engineering mathematics that we are just revisiting here. In the same way, if you have a vector like as we represented previously like this, if you have a two vectors, if you are writing this vector in the matrix form, this is say u1, v1, w1, and you can represent this as also u2, v2, w2. So if you are writing means u1, v1, w1, you should able to think that you are representing some vector as a matrix form. These two vectors that we are representing in a matrix form, and it is again one-to-one addition. This is how the matrices formulation are very useful in our entire CFD course, not only for the small practice of this vector form, but also solving big system of equations that we will see in the later on courses. And suppose a scalar value that is say 10 some units, some 10 units, s is equal to some 10 units. if you are multiplying a vector, suppose this vector has a magnitude of 20 units, 20 units, and you have this x direction, y direction, and z direction. But your vector actual direction radially moving in this direction, that means it has some u component, v component, w component. So I want to increase its magnitude by 10 times, that is 200 units. That is 200 equals to say 20 times 10, that is 200 units. I want to increase it by 10 times. How you can increase? That is just multiplying a scalar value, a single value that doesn't have any direction. You can just multiply with that and you can increase its magnitude in all the respective directions. That is, if you are adding a scalar value to this vector, that is s equals to 10 units, it will increase its magnitude in x, y, and z directions respectively. How is? Just you multiply s times v bar equals to s into u I cap plus s into v j cap plus s into w k cap. So this is how you can add or you can increase the magnitude of a vector. So once you are done, then we have few properties like dot product, cross product. It's a very familiar words to you, but I just revisit and we will see at the end of the session how these dot products can be seen in another level of understanding. Like we know that I dot I, that is I cap dot I cap. I'm just um, directly saying with keeping in mind that you already visited these kind of notations in your physics or mathematics classes. So I'm not going to details of what is this I cap because it is already you know that it is a unit vector in the direction of x. I is the unit vector in the direction of x and j is the unit vector. Suppose this is x I cap, y j cap, and z k cap. So I dot I will give you a unit vector, that is I dot I we are multiplying, that is equals to 1. In the same way, it is valid for j dot j. At the same time, it is also valid for k dot k. Okay. So what does dot product indicates? Why dot product we need to do? What are the other product we have? We also have cross product. I dot I cap cross j cap is equals to k cap. It will follow some syntax that we can use it. But how we are deciding this? Suppose if I have a unit vector, this is my vector a bar and this is my vector b bar. If I'm going to do the dot product, I will say a bar dot modulus of a bar. This is a modulus symbol. We are using now only one braces. A bar dot b bar dot sine of, sorry, this is not a sign. A bar dot b bar dot cos. Is it right? Yes, a bar dot b bar dot cos of theta. That is, theta is the angle between these two. If your angle is 0 between these two, then only you will get a true product of a dot b bar. That is direct multiplication of magnitude of a vector or b vector. Now see, I am doing a cross product between I dot I. I means is the vector in the x direction, and this is also I is vector in the x direction. So the angle between two I, that is this is one I and this is same I, same direction. What is the angle between these two vectors? Is just 90. Sorry, 0. I'm sorry. It is a 0 degrees. So if your angle theta equals to 0 degrees, just substitute theta in this. That is magnitude of I cap dot magnitude of I cap cos of 0 degrees. We know that cos 0 equals to 1, and it is been saying that it has been saying that I cap is nothing but a unit vector in the x direction. If unit vector means, what does it magnitude means? If you are trying to find the magnitude of a unit vector, that will give you 1. That is 1.1 cos 90 is 1 is multiplication. That is just will give you a value of 1 unit. So that is why I dot I will give you 1. If you are multiplying with any other vector, I dot j cap, what it will give you? It will give you a 0, because you just see the angle between these two. The I dot j cap is this way. I is this direction and j is this direction, and your theta is 90 degrees. If you substitute theta equals to 90 in the cos, you will get 0. So that I dot j cap will give you a 0. Okay. Let's see the cross product. If you are doing the cross product, I cap cross j cap is equals to, we are having a k cap. How can you do this k cap? It is just, again, if you want to find out the magnitude of this k cap, it is just modulus of I cap cross modulus of j cap, and then you will have sine of theta. Theta is angle between I and j. I is in x direction. Now we are doing cross product. Keep in mind that earlier we did the dot product. Now we are doing the cross product. I cap cross modulus of j cap times sine of 90 degrees. What it will give you? It will give you a unit vector only, because modulus of I cap is 1, modulus of j cap is 1, sine 90 equals to 1. So it will give you just some unit vector. But here you see all are in modulus. It is not giving any direction. So how to identify the direction of it? How we are saying it is in the k cap direction. So before going the details of it, it is very interesting to know how this dot cross product works. Suppose you have a velocity vector v1 equals to u1 I cap plus v1 j cap plus w1 k cap. This is how, say, your velocity vector v1. And if you have a velocity vector v2, v2 equals to u2 I cap plus v2 j cap plus w2 k cap. And if you are trying to identify the cross product between these two, what will you get? The cross product definition says you should find the determinant of between these two vectors by the format I'm just writing. u2, v2, w2. Substitute that your cross product vectors in this format. First the unit vectors, that is I cap, j cap and k cap, and then substitute your unit vectors magnitudes that in all the directions, that is u1, v1, w1, and then u2, v2, w2. If you try to identify its complete form, if you try to define its entire determinant by using some determination formulation, you will get a determinant form of the entire things. Let us write that if you are having this I cap equals to, like, I will just say I cap, and we are using the remaining two as a product, that is v1 a into d minus bc minus j cap, and then a into d minus w1 u2. So this is how you can expand your definition of the things. Okay, we are just now doing I cap and j cap. We don't have any magnitudes of this. So if you see the k cap definition, the last thing is which involves only u1 v2 minus v1 u2. You see, in our vector I cross j cap, we don't have any w product, right? I means refers to the x direction and y refers to the y direction. J refers to the y direction. There is no component that representing the z direction. So here the w is the component that represents the z direction. So you won't get, it is not possible to get j cap and I cap. So what will you get? Because here you don't have any values that is corresponding to the w cap, so that you will get only the k cap. You got it? And you remember that your components are only unit vectors. It's not a distributed one. As you don't have the w product in your vectors, it is only purely x and y. These components will go away as you don't have the w product. So only you left with the x and y products, that is x corresponding to u, y V, and this is also V and U. So that's how you will get I bar I cap cross j cap is equals to k cap. So this is the idea of your cross product, but we have some more details of if you multiply, but the additional property is j cap cross I cap is equals to minus k cap. You should able to see by yourself like how these things are playing in the matrix. If you write these things able to, and if you are able to write these things in the matrix and you're able to derive this, you can easily understand why we are getting this minus. By simple definition, from the actual definition is we have I cap here, j cap here, right? You have x direction is this one, and y direction is this one, that is j cap. Earlier you did I cap cross j cap, that is you are going from anti-clockwise direction, starting from here and up to here, this is your 90 degrees. Then you are getting I cap cross j cap modulus into sine of 90. If you are going in the backward direction, j cap cross I cap, that is in the clockwise direction. What is our clockwise sign convention? That is minus 90. Okay. If you substitute the same, your modulus will not vary. But your sign convention says sine of minus 90. Sine minus 90, it is not a cos to like to make it as positive. So it will give you the negative k cap. So these are the key manipulations or key mathematical factors that you should able to practice on your own to understand the in-deep vector calculus importance, that how it is playing with respect to unit vectors. Suppose if I have a velocity vector v1 that I wrote already, v1 u1 I cap, that v1 j cap. I've been telling a unit vector, unit vector, unit vector in many times I told, but if I want to find the unit vector in some direction, this is my v bar and this is my z, this is my v1 bar. If I want to identify the unit vector of this v1, unit vector means I just want to only the direction of this v bar, but not its magnitude. So what we should do? We should do by we should make the unit vector by create the unit vector by dividing its vector with the magnitude of the same. If I want to identify the unit vector of v1 bar by modulus of v1. So if you do that, you will get the unit vector. Say, I will just indicate it's a unit vector v in the direction of v1. That is e cap in the direction of v1. So this will give you the unit vector. That is whatever the value you are getting is will be in this format: u by u square plus v square plus w square I cap, and v by where this u square, v square, and w square is your modulus that you are dividing with your entire vector. And this is your k cap. So this is how you can identify the unit vector, right? So let's go for the further details in this session. Let try to understand some basic properties. Uh, let me give you some basic properties of these vectors. Okay, here it is. Some identities in the vectors are like this. Okay, before going to the identities of this vector, I have to give you the introduction of the gradient, divergence, and a curl of the things. What are these gradient and divergence and curl? So we generally denote a nabla like this. What does a nabla mean? A nabla is equals to dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. This is a common parameter that we use, which can be used as a gradient or which can be used as a divergence also. But what are those divergence and gradient, how we are handling it based upon the product that we are doing. Just remember that it is a nabla, then its operation is the partial derivative of a some variable, whatever you're using. Suppose if your variable is pi, some variable in the flow field or whatever it is, then you just substitute all your pi here. So what we are doing, we are just doing the partial derivative of this pi in I direction and j direction and with respect to y and k direction with respect to z. Let me tell you what we are doing. Suppose you have a flow field in the xy domain. In the xy domain, this is your domain, and you have a flow field, and you are measuring the pressure at every point. Suppose this is a pressure, and say, uh, suppose 2 pascals, and you're measuring the pressure at different points. Okay, this is your flow field, and you are measuring your pressure in the entire flow field. Suppose this is a 2 pascals and it is a 3 pascals. It is not the physically possible flow field, but I'm just telling this is a 2 pascals, 3 pascals, and say at the center you are having a 10 pascals, and at the corner, this corner you are again having a 5 pascals. So like that, your pressure field is distributed. This is the pressure in the flow field. And now my pressure I'm denoting with the letter T. Now what I'm going to understand is if I'm standing in this position, suppose at this position A, at what direction if I move, I will reach a maximum pressure zone. By the physical sense, if you are able to see the details of the flow field, one can easily say, if I move towards this direction, that is a vector in this direction, I will reach the maximum pressure zone. But how do you say it mathematically? To say it mathematically, one should have a function of pressure. Suppose P equals to P of x comma y. That means if I substitute x equals to say this is 3 and this is also 3, that is x equal. If I substitute p equals to p of 3 comma 3, that means if I substitute in this function, that is p of x comma y, some function that we are not bothering about, some function we are substituting the values 3 comma 3, that is x equals to 3 and y equals to 3. This function should give the value of 10 pascals. That is what we call as a pressure field, this kind of function. The function that represent your pressure field, we call it as a pressure function field. So one should have this kind of function and they should be able to evaluate at every point. See, we have points from ranging 0 to suppose this is a 100, and these are not reasonable scalings, but I just for your understanding. So from 0 to 100, you are moving in x direction, 0 to 100, you are moving in the y direction, and your pressure is varying in the entire two-dimensional flow field. That is like center, you are at some 3 comma 3 location, you have a 10 pascals, and you are standing at a position of 5 comma 5, x equals to 5 and y equals to 5. And I want to move to the location where there is a high pressure location. So how you can identify the direction? Just by looking the values, you can identify, or also mathematically how you do it, you just need to find its gradient. That is what the gradient helps you. Like if I do the del P, this is my pressure, and del P, I just need to partial derivative of this x with respect to x comma y. That is I cap. At the same way, partial derivative with respect to y and put it as a j cap and put it as z cap. So if you do this partial derivative and substitute this I, j, k caps, this will give you a vector. Suppose some vector it is going to give. That vector is the direction where you can see, or if you move in this in that vector direction, you will reach the maximum pressure zone. So that is how your gradient helps you. Fine. So it is a key vector calculus parameter that we will see these kind of parameters more in details. As we have only 1 hour, I will just introduce few more parameters. That is like this is del P equals to dou by dou x of P of x comma y. This is the pressure field. If you do the same thing but with a dot product with a divergence, Divergence means you just do del dot V bar. Here your pressure is a scalar. Here your velocity is a vector. So that's why we are telling it as a divergence and you're putting it as a dot product here. And how will you handle this? First, write the dot product formulation according to this. We have I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z, right? And then put the dot product u I cap plus v j cap plus w k cap. According to our dot product formulation, we just need to substitute 1 to 1. And then if you substitute 1 to 1, remember what will happen. I cap dot I cap dou by dou x of u, this is one term, plus j cap dot j cap. We are just multiplying with dot creating dot product with 1 to 1. 1 to 1 means this I cap, this first term will participate with first term, and second term will participate with second term, third term will third term. So, and then you will have dou u v by dou y plus k cap dot k cap dou w by dou z. Right. Now you see we already know I cap dot I cap equals to 1. This j cap dot j cap equals to, this is also 1. This is also 1. And then you just see dou u by dou x plus dou v by dou y plus dou w by dou z. What you get? We did not get any kind of vector as we seen in previous here. Here we got a vector. That means, and here we are getting a scalar because there are no I, J, K components. We are getting some kind of value, some numerical value without any vector direction. So the way you are using this nabla and whatever you are multiplying in its side is the key that denotes whether you are getting a divergence or we are getting a gradient. A gradient indicates a direction where you are having a maximum amount of that uh, scalar value in the flow field like this. This is the maximum value location in that scalar field. But a divergence indicates some kind of scalar value. If you do multiply, if you do a dot product with this nabla with this operation we are calling as a divergence, that is nabla dot v bar. If you are doing this, you will get a scalar value that is dou u by dou x plus dou v by dou y plus dou w by dou z. You are getting a scalar. So how it is helping us? What is now this one is indicating in the flow field. If you have a flow field that has a velocity vectors, suppose I am generating the velocity vectors like this. If you're generating a velocity vector like this scalar product will give you this scalar value. What is the last scalar value that you are getting? That will give you the idea of the amount of product or the content or the mass content that is diverging from that point. It is bit unclear to understand directly from here, but as we go with the more mathematical terms by taking it as a granted, we will see in details in the next soon coming up classes that how this divergence is creating or helping us by understanding the amount of mass flow rate generating at that point. Suppose if your divergence is 0, dou u by dou x plus dou v by dou y plus dou w by dou z. If your divergence is 0, you will get a 0 mass flow rate at this point. Though we are having a velocity vectors in this rapid direction outward, velocity vectors are all rapidly moving in the outward direction. That means you should have some mass flow rate emerging from this point. But if your divergence, that means at this point, if you are saying like this amount of mass flow rate is coming out, then there should be a finite value of divergence. That whatever the fluid is emerging from this point, that should be some finite amount of say 10 units. Then how do you calculate? We have only the vectors here, vectors as a function, vectors v equals to v of x comma y. You have only the vectors as a function at every point like this. Then how do you calculate that? Then you just substitute this vector as same as we did for the scalar field in this terminology. And if you get a finite value of divergence, then means there is some flow field emerging at this point. That is a physical reason or physical meaning that you will get from the divergence. In the same way, we also have in addition to the gradient and divergence, we also have the curl of the product. What does this curl mean? Curl indicates del cross V bar. This we already did. Curl means the cross product of two vectors can be given by I cap, j cap, k cap, and you will have dou by dou x, dou by dou y, and dou by dou z. Here you have u, v, w. Right. You just need to find this determinant to get this del cross V bar. This will give you whether the fluid is rotating or not. Fluid rotating means earlier I drawn the fluid elements are emerging from a single point. There is no vector that are rotating like this. So this curl, whatever the curl equation that I wrote here, will give you again some particular vector format, but that magnitude of that vector will give you an understanding whether that fluid is rotating in the flow domain or not. Rotation means we can see when there are spiral is happening, a hurricane is happening, those kind of spiral rotation, everything is different terminology, but I will just say both are like looking same. And if you are having this kind of rotational flow in the flow field, then that will give you this value or the strength of the rotation you will get by the curl of the velocity vector. This is your, if you say velocity vector is any vector that you are indicating with a v bar. If you find the curl at that point, that will give you the rotation strength. Okay. So these are the uses of curl, divergence, and this gradient. So now some important definitions I will just write for you. These are like I can give you this these definitions, but few things I will write. That is del of del cross v bar. What if we do the curl product and then the dot product to that? That will give you 0. Okay. And the same way, if you are doing curl of gradient of a scalar product, this also will give you 0. Okay. If you are doing the dot product of some vector that was multiplied by with a scalar, you can write it as s del dot v bar plus v bar dot del s. You don't need to remember all these things, but we just need to see these are all called as the vector identities or vector calculus identities. You just need to see all these equations and how they are behaving. So I will forward these all these equations for you, maybe through some uh, material in some Google folder. You can just have a look of these things. Okay. So this is a basic idea of your vector calculus, but why we need the vector calculus and how it is additionally helpful to us. Suppose I have a two vectors here like this v1 bar and v2 bar. Why I need to do this? This is the origin or some position. These two are emerging from this position, and instead of say velocity vectors, I will say position vector r1. Position means we are indicating the positions of the particle here and the particle here. This is r1 and r2. We have an origin here. Now, what I want is I want the area by like this, or I want area by joining these points, the point 0, r1 and r2. I want the area of this triangle. If you know the dimensions like this horizontal line and vertical line, then you can use the half BH formula. This is commonly that we use. But how we can do by using the help of a vector calculus? You can do this by using the cross product from 0 to r1. Okay, we will a recent reference I will give you how you can calculate that area of vector, sorry, area covered by these two vectors, like this triangle. If you do the cross product will give you the entire area. Like if I am having a vector here like this and a vector here like this, if you do the cross product between these two vectors, that cross product will give you the area that I just hatched. Okay, R1, R2. Then if you are multiplying with the some other vector that is in this direction, multiplying means now you need to do the dot product. Dot product say R3. Now R3 dot R1 cross R2 will give you the volume. Will give you the volume occupied by, or volume in this kind of parallelopoid. It is a bit not clear to draw. So this will give this kind of simple formulation, that is R3 dot R1 cross R2 will give you the volume of a parallelopoid. That means we also able to see, or we also able to identify, if you have a polyhedral or if you have a tetrahedral, some shapes, these kind of things. We just need to identify its coordinates of x1. In the true plane or any basic shapes, if you see a square or a rectangle or a parallelogram, you can easily able to calculate its area, or if it is three-dimensional, you can calculate its volume based upon its dimensions like length, breadth, and something. But if you don't have anything, details like length and breadth, but you only have the coordinates like this, and the shape is very complex, like the coordinates of 3 comma 2 and 5 comma 6 and 10 comma 8. There will be a jet coordinate also, say 9 and 3 comma 3, 2 comma 4 comma 3. And now your question is just find out the volume of this product without having any dimensions not given clearly. You don't need to how you, but we just have only the coordinates of 3 points here and 1 point here. We don't have any other details of this uh, shape. Then how we can calculate the volume of this fluid? In computational fluid mechanics, the generation of these kind of volumes, like volumes generate, we generally do generation of volumes by just only identifying the coordinates of these points, but not using the shape of the element. So how do you just find out this volume by using this only the points? Is just again using this uh, formulation, that is R3 dot R1 cross R2. You just need to do cross product of two vectors and a dot product of the third vector that is in the plane perpendicular to these two. This will give you a parallelopoid, or you can also make it as tetrahedral. You can also identify it's a tetrahedral shape volume. First you will get from these two the area of the shape, and then if you multiply the third coordinate, then you will get the volume. After multiplying this, you will get the volume. Numerically, how we can do these kind of steps is can be better understandable by solving some problems. Um, Let me show you the problem. So here is your first problem. Here they are asking us to find the, or find the area of the triangle. You see, you just need to find the area of the triangle only by having the points P1, P2, P3. You don't have any other points, and these points are not along the x direction, or not along the y direction, not along the z direction. It is random in points. Say P1 bar and P1, P3 bar, like that. Some points only we have. Then they asked us to find out the area of the triangle. How you can find it? These are looking uh, unrealistic, that you find the area by just using the by just using the points. So what you can do is you can first make this triangle like the shape of a parallelogram. This is the shape of the parallelogram. if you have the shape of the parallelogram and you have a vector, this vector and this vector. Vector means just the positions only. So what are those positions? X equals to 0, y equals to 0, z equals to 0. We need a vector of from P1 to P3. P1 to P3 means these two. Okay, based upon these two. And we need a vector from P1 to P2 that is based upon these two. You just need to subtract the details to just get exact dimensions of or exact distance from P1 to P2 and P1 to P3. Then you will get the vector like this, x2 minus x1, that is P1 P2 vector and P1 P3 vector. Once you get P1 P2 vector and P1 P3 vector, just do the cross product. How do you do the cross product? Like this is what the first vector you got, and this is like the second vector you got. Then you will get the area of the complete paralleloid. Sorry, complete parallelogram. Once you get the area of this complete parallelogram, what you need to do, this is a parallelogram, and if you are having a diagonal like this joining this one, then you will get the only half area of that. That is why we are using the 0.5 here. Okay, this is how you can find out the area of a triangle just by using the points. You don't need to use any other techniques. This is a very helpful technique. And I already told you we can find the volume of a paralleloid also, and that is here. So if you want to find the volume of a paralleloid, how you can do this? Again, we have only the data. In the earlier, we have the data of P1, P2, P3. Now they just give the additional data of P4, right? And asking us to find out what is the volume of this pyramid. So now you cannot directly get the pyramid like by using the cross product or dot product. You just need to construct a paralleloid. It is bit like paralleloid means you just need to construct this kind of shape. If you cut a pyramid like the triangular pyramid as you're seeing in the figure 2.6 from this paralleloid, you will get a factor of 0.25. That means the volume of this pyramid in this paralleloid is 0.25 times the volume of the above. Okay, so that's why we are getting a 0.25. First, you need to calculate the area of the bottom from by this vector and this vector, just as we did previously. Once you calculate the area based upon this vector and this vector, just hatch the area. Now we found out the area. Then you need to find out another vector that is in this direction, that is area of, sorry, the length that is perpendicular to this plane or whatever the plane it is. We cannot no need to be perpendicular, but you just need to find out the another vector that is uh, in the volume direction. So that is that another vector you can find out by the using this is, if you say it is P1 and it is P4, then you just subtract the values of x values and y values corresponding values, that you will get the P1 minus P1 P4 vector. If you do the dot product to this area, that means we are just multiplying P1 minus P4 means some length. Then we are already having an area here. If you multiply length time area, it's not a dot product means we're just multiplying again. So each value will be scaled up. Then the corresponding output will you what you will get is the volume of this paralleloid. But you should remember that you should multiply with the 0.25 because this pyramid volume is 0.25 times of the volume of this paralleloid. Okay. So that is what we want to cover in this session, but a few more theorems like Green's theorem, line integral, Stokes theorem, those things are also there. Divergence theorem that we can see while taking up the corresponding. We can see those functions or those definitions while taking up the corresponding concepts in the upcoming classes. Okay. So that's all for the today's class. If you have any doubts, you can just ask for a few minutes, a few quick 2-3 questions we can take for the today's class.
Dear students, if you have any doubts, please ask.
These
If you
sessions
don't
are
have,
recorded. Yes,
sir.
sorry. These sections
I-
are recorded. If you want to find out these sessions, I will upload in YouTube. You can find out these sections once again. We'll share the link to the Prabhakar sir, and you can find out these YouTube's links again, and you can refer those material. Thank you, sir. Please proceed.
Okay, sir. Thank you, sir. Thank you very much, sir. So we'll end this session for today, sir.
So, sure,
So
sir, sure.
Saturday
No
same
question.
time we'll meet again. Sir.
Saturday same time we will. Sure, sir.
Okay, fine, sir. Fine. Thank you very much, sir. Thank you,
Thank you, sir.
Nagendra Prasad Garu. Thank you.
Thank you, sir, for your coordination. And
Okay.
if students, whoever were very interested, they can join. And if they are not interested, maybe we can talk in personal, sir, over a call.
Okay, sure.
Thank you, sir.
Sure,
Thank you,
sir.
Prabhakar,
Okay,
sir.
thank you very
Okay,
much, sir. Thank you,
thank you.
sir.